Okay, so welcome. This is the second chapter in this 4-chapter sequence, and this is on waves. So last time we did oscillators, which was a single particle, if you like, and its history in time. And now we're going to connect a whole bunch of oscillators together somehow, maybe by bouncing into each other, maybe by elastic forces. And so the energy of one particle, one oscillator, affects the energy of the other oscillators, and they form a unit. And so we get waves. So a whole group of oscillators together make waves. And you can look at a wave and say, what's that individual oscillator? What's that particle of water doing in time? It's going up and down like an oscillator, but the crest of the water surface is acting like a wave. So we're going to introduce a whole bunch of new language and terms and symbols, and some of them are Greek letters, and some of them are little curly bits on top. And I can tell you now, the math is not that hard. There's a little bit of trig, but it's just can you figure out a sine or a cosine? The math is not hard. For most people, it's the unfamiliarity with the language or the symbolism, the Greek letters. That's what puts people off. So it's really important, I think, that you recognize that and you spend some time and get familiar with it. So don't do what I did, which was I ignored all that stuff and just said, can I solve that math problem? And I could, and then found when the test came and they used these terms, I wasn't really sure what the terms meant because I'd not studied that. I'd studied the math, which is, can I do a sine? Can I figure out what a sine is? Well, of course I can figure out what a sine is. The real trick on this is getting familiar and getting comfortable with these terms. We've seen some of them before. So first thing we're going to do is classify the waves into different types, and we're going to talk about longitudinal and transverse waves, and we're going to talk about wave trends and wave pulses. We might have done that in fundamentals. And then we're going to talk about the characteristics, and we're going to talk in terms of amplitude. We've been there before for oscillators. Period, we've been there for oscillators. Frequency, we've been there for oscillators. Angular frequency, we've been there for oscillators. But now we're going to talk in terms of, in addition, wavelength, a thing called wave number, and a thing called angular wave number. And I'm going to give you a tip off the bat. If we put oscillators at one side and waves, well, our amplitude for our oscillation is going to be the same as our amplitude for our wave because the wave is made up of oscillators. So if I think about my period for my oscillator, how long it takes to go through one cycle, the equivalent in waves is wavelength. That's a Greek letter lambda, and it's like a Greek L. And it's for wavelength. And remember what we said? We said, well, I'm sick of talking about really short periods. I want to talk about the inverse of period and call that the frequency. So I had frequency, hertz. The inverse of the wavelength. How many wavelengths do we get in 1 meter as opposed to how many oscillations do we get in 1 second? The equivalent for that is the wave number. It's a mu. Or a nu, it's a nu with a little curly thing on top. And the last thing is, we found it convenient because circular motion can be used to describe oscillatory motion. We found it useful to talk in terms of our angular frequency, which was in radians per second. That was our omega, little Greek W if you like. And that was in radians per second. The angular equivalent for the wave is K, which is our angular wave number, and that is going to be in radians per meter. Radians per second for angular frequency, radians per meter for angular wave number. And the relationships, if I told you, I hope you're learning that omega equals 2 pi times f. Well, k is equal to 2 pi times that guy, angular wave, times the wave number. If I told you that omega is equal to, if I told you that f is equal to 1 over t, I hope you can see that wave number is equal to 1 over lambda. The analogies, they're very similar, so we'll get to that. But there's a lot of new ways of looking at things with new terminology. So, and it's not mathematically hard, it's just inverses and the like, simple stuff, but it's very unfamiliar. So break it down, get to know what the things mean. And I'm not above asking you, so, you know, frequency is to period as wave number is to wavelength. I mean, just stuff like that, because do you know the definitions and the like? So we'll do that. We'll talk about one-dimensional traveling waves. And we'll try and get an idea for an equation for those and wave speed. And we'll try and build a model of waves so that we can say what's going to happen at this distance from my starting point at this time in the future. So we'll try and do that. We'll play with these things. We'll have waves on a string. We'll talk about the speed of waves on strings. We'll talk about reflection of waves, transmission of waves, and we'll talk about energy transfer. So there's a whole bunch of stuff that we're gonna go through. Now let's do it step by step. So 2 types of wave. There's the longitudinal wave and the transverse wave. The medium, we're talking about mechanical waves. Don't go into light and don't go into stuff like that, because we'll get to that. Just think in terms of, I don't know, waves on a string, or spring, or waves going through the air, or waves going through the water. And in each case, there's a medium. The medium is the water, or the air, or the string, or the spring, or something. We need that. The wave is the energy. When I speak to you, nothing from me reaches you. The air doesn't come out my lungs and go into your ear. That would be totally disgusting. You'd be like sick all the time. The air just stays in my throat, and it pushes the air in front, which 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 pushes the air in your ear. It's the energy that's gone from me to you. It's not the mechanical stuff that's gone from me to you. It's the energy. So the wave is a manifestation. It's a unavoidable consequence of the energy transfer. That's what the wave is about. And there's 2 mechanisms. One is the transverse mechanism and one is the longitudinal mechanism. The longitudinal mechanism is just things bump into each other. So air particles, they're not connected, they just bump into each other. And so I get a high pressure bit and a low pressure bit, because when I bump, I leave a gap behind me, so I get a high pressure bit and a low pressure bit. And that energy, I bump into you, you bump into the guy in front, you bump into the guy in front, and so on. That energy goes through the medium. The displacement of the medium is on the same axis as the energy transfer. The particles go backwards and forwards along the line. That's longitudinal. In a transverse wave, we have to have elasticity, because I'm going to push the particle to the side and it's got to spring back into its position. So that would be, if I take a string, I can in fact show you this. Can I get, will you do me a hand, will you give me a hand? So let me take that and I'll go to this end and hopefully won't knock it. Yeah, we always knock them. That's an annoying thing. Okay, so what I'd like to do is hold it relatively high and hold it firm, okay? So what I'm doing is I'm tensioning the string. So there's elasticity in the string. And what I can do is I can send a ripple of energy. Every now and then we're going to hold it like that just to try and get the energy away from it. So I'm going to send a ripple of energy through, and none of this metal goes over there, but something does because you can see it. If I make this slacker, then it's a little bit slower. You hold on tight. If I make this tighter, it's faster. So the speed with which the energy goes depends upon the properties of this medium. We're going to get to some stuff in a bit. Okay, so that's it. Let's just put it on the ground because we'll play with it a little bit more in a bit. So those were transverse waves, and you only get transverse waves when you have elasticity. So you don't get transverse waves through the body of a liquid, but you will get them on the surface of the liquid because of the surface tension. So, okay, so we have, and in transverse waves, the medium moves at 90 degrees to the energy direction. Okay? So in longitudinal, the medium moves in the direction of the energy transfer. In the transverse, it moves at 90 degrees to the energy transfer. Okay, then we have two types of waves. We have transverse and longitudinal, and then we have two, if you like, mechanisms. So we have a wave pulse and a wave train. And a wave pulse was what we did. I pulsed it, and it went, and you could saw it coming back. Wave train is if I'd kept on oscillating. Now the problem with that, the reason why I didn't demonstrate that is because as soon as it starts reflecting back, then we get a complicated situation. So it's hard to demonstrate that. But I can visualize it. So this is high compression, 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 just going on and on like that. That's like if I go, that's a longitudinal wave train. If I go, that would be more like a longitudinal wave pulse. You could argue and say even that has a lot of waves in it. It's not just one wave. It's like a lot of stuff. But a short, very short little bit, is a pulse. I could flick this thing, I get a pulse. I can do a continuous thing, and I get a wave train. I'd like you to be able to understand, to explain, to pick out examples of wave trains, wave pulses, okay? And also longitudinal and transverse. So, if we look at this, classify the following waves. A single ripple on the surface of a water. What would that be? It would be a transverse wave pulse, yeah? So it's a trans pulse. Sound of a continuous whistle. I can't whistle. It's going to be long train, yeah. Okay, and so on. Okay. This is kind of interesting. This is a little bit of an aside, but it's really valuable. So here's the Earth. We have a crust. We have a thing called the mantle, which is like warm asphalt or semi-molten rock. And then we have a liquid core and a solid core. This is solid iron. This is liquid iron. And we know that because we cut the Earth into and had a look inside. I mean, have we cut any planet into and looked inside? Have we even got through the crust? Absolutely not. We've not got through the crust. Sometimes the mantle leaks out, but no one's gone down to look. So in terms of evidence, show me the evidence. There's no direct evidence that that's the case, although there is other evidence which is compelling. And one of the things is that when there's an earthquake, we know where the earthquake is because we have seismology stations basically all around the Earth now. It used to be in some places, and now we have them basically all around the Earth. And what happens is, when we get energy released in an earthquake, the energy goes whatever way it can. It wants to get away from that initial point, and there's two mechanisms open to it. There's longitudinal wave energy transfer and transverse wave energy transfer. And it turns out that they go at different speeds. I want you to imagine a whole bunch of people in line, shoulders, my hands are on your shoulder, my arms are stiff, and they're facing that way, and I come and I push the person at the back. And that's a model of a longitudinal system, yeah? Everybody's got their arms straight, and I push you, you push the guy. And then the other thing is we've all got our arms interlocked, so we turn sideways, our arms are all interlocked. And then I go to the end and I wiggle the person at the end. And then that person wiggles the next person. Which do you think will go fastest? Do you think it will be the longitudinal push, or do you think it will be the transverse wiggle that goes fastest down the... It's longitudinal. It's much more direct, isn't it? It turns out that's exactly the case. So, for instance, in geology, the long is called the primary because it gets there first. And the transverse is called the secondary. And the way I remember it is transverse has an S in it, but longitudinal doesn't have a P in it. So it's just the way it is. But, So what happens is all these seismological stations get the time difference between when the primary comes and when the secondary comes, and they know, oh, this event is so far away from us. So they draw circles. So this guy knows it's on that circle, and this guy here knows it's on that circle, and so on. So that guy knows there, and this guy knows here, and this guy around here knows there, and that guy there knows there, and so on. Yeah, they go on. Because they're looking at the primary, secondary, primary, secondary, primary, secondary, primary, secondary, primary, secondary, primary, secondary, primary, secondary. And because they've got so many stations, they can really home in now on where this thing is, how many miles it is below the surface, and exactly where it is. They can really find it really well. They've got 1,000 data points rather than 10 data points. It really works well. Interesting thing happens. Around here, you only get a primary, you only get the 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 primary. It's like there's a shadow. It's like, whoops, I didn't draw this very well. It's like there's a shadow. And the shadow is, you don't get any secondaries going in that bit. Now, secondary is transverse. Transverse cannot go through a fluid. Oh, there's an ocean of fluid inside here. So that's really good evidence why there's it doesn't matter where the thing is. If you have the earthquake up here, you get the shadow on the other side. So you don't get secondary waves on seismic stations on the opposite side of the earth from where the event took place. Why do we know why do we think there's a solid core in there, and why do we think it's iron? There's a number of reasons. First of all, iron is the most stable nucleus. So in the scheme of things, that nucleus is very long-lived. It's a nice stable nucleus. And also, we have a magnetic field, and we believe we get the magnetic field from the rotation of charged particles. And so charged particles are created in an iron core when it's really hot. So we have a spinning iron. Well, really, we have an iron core which is spinning. It's been pulled by the viscous drag of the liquid core. And that's why sometimes you get this change in orientation, which changes your magnetic field. So no one's ever cut the Earth open. No one's ever seen this, but it all pieces together, and so they've got a reasonable idea for what's inside the Earth from this kind of information. Cool. This is a really important page, and it's worthwhile spending some time on. We've touched on it already. On one side, I'm distinguishing, I'm sorting out the oscillations, and on the other side, I'm talking about the wave. Think of the oscillation as being a graph of position versus time for one particle. It's one particle's history in time. And think of a wave as being a snapshot of a whole bunch of particles at one instant So one is an abstraction, it's a graph of what happened to this particle. And the other is, let's take a snapshot of all the particles now. They're completely different. And yet they look identical. This is a graph of y position versus time. And this is a graph of y position versus x position. So they're completely different things. And yet they both look like sine curves. They have the same amplitude. So it's very easy to get them confused. And they tend to be taught together. And I think the book does a good job of saying, this is oscillation. Now let's put oscillators together, and this is waves. We've talked about oscillators. We said there's an amplitude, and the amplitude goes from the equilibrium position to the extreme. We've talked about period, and period is the repeat time. Crest, well, not crest to crest. It's the crest of this graph. It is, let's call it the maximum to the maximum, or the minimum to the minimum, or the zero going upwards to the zero going upwards, or the zero going downwards to the zero going downwards, but not the going upwards to the going downwards. That's a common mistake. People will say, that's the period, when it's not. The repeat is there. You've got to have the graph going in the same direction. That's period. Certain number of seconds. You don't really need frequency, but people don't like really small numbers. So if rather than saying how long does it take for one cycle, if you say how many cycles can you take in 1 second, it's the opposite, it's the inverse. And so we like frequency. When I was a student, it was called cycles per second, and then they named it after Hertz, which lost some of the meaning to some extent, but it's cycles per second. It's commonly called Hertz. So we made that up, but it's kind of like nice every now and then. They're interchangeable. Period and frequency tend to be interchangeable. They don't mean the same thing, but one's easily derived from the other. And then what's not so obvious is that because one cycle is like 1 times round our loop in our circular motion, yeah? One cycle is like once around the circle. We can talk about a fraction of a cycle as a fraction of a circle. And so we can represent cycles per second as radians per second. Rather than one cycle, you have 2 pi radians. So it's useful to introduce this idea of angular frequency. And if you're anything like me, I'd say, man, I do fine with Hertz. I'm not even bothered with this new thing because it's just like they're doing busy work. And that's not true. Nothing in your book or in my notes is there just to kind of occupy you. It's because it makes you more powerful. So this is an important thing. In fact, this is quite important. We tend to use this probably more than we use Hertz. Okay. Now we take a whole bunch of oscillators, and each one's going through its cycle. It's going like that, and the next one's going like that, and the next one's going. But we combine them. So the first one pulls on the second, which pulls on the third, which pulls on the fourth, and we get a wave. And when you look at this, it looks kind of like the same as the graph, but this is a snapshot. Again, we can talk about the amplitude being from the equilibrium position to the extreme. But now the repeat is not a time. The repeat is a distance. And this is our wavelength. It's the crest to the crest, or the trough to the trough, or the equilibrium going upwards to the equilibrium going upwards. It's that, but not the equilibrium to the equilibrium. Yeah? And we could talk about just wavelengths. It's measured in meters. And then people say, but I don't like really small distances, so I'm going to not ask how long is a wave, but ask how many wavelengths do I get in a meter. And so that becomes our wave number, and spectroscopists use that a lot. So it's used a lot by some people, and we use it a fair bit. It's just like frequency. And then because this circular motion is very good for describing the oscillatory type stuff, we can have the angular wave number, and that is the number of radians of oscillation in a meter. lot of analogies and equivalencies there. And what I've done is I'm like really comfortable on the left-hand side, and if in doubt, I use analogies on the right-hand side. As we'll see. I'm going to show you this in a minute. So we have period is like wavelength, and frequency is like wave number, and angular frequency is like angular wave number. Big problem about K, because we just used that last chapter with a spring, and we call that the spring constant. And now we're going to call it the angular wave number. And it's K. It's not even like they weren't even decent enough to give it this, like, you know. It's a little K, just like the other one is. So there's nothing wrong. You can't call it J just because you choose to do it. It's going to be totally confusing. So you've got to leave it as K, but there's nothing wrong with you putting a little subscript on it, you know. K spring, K angular wave number. Or you could have K with a little blurry bit and K with, you know, you can dress it up. But I would do something, especially at the beginning, to make sure I'm not kind of like just writing all the K's the same way. It is from context. It's like, you know, you don't get confused about drinking a cup of tea and hitting a ball off a tee. They're not even spelled the same way, are they? That's not a good example, but, you know, bark and bark, you know. You don't kind of go, oh, that dog, you know, what does a dog do? A dog barks. What, it makes the skin of a tree? No, you know the context. You're not going to picture a tree when you talk about a dog barking, you know. So we're used to using context, and this is the same. It's just we're not used to this bit, so it's a little bit uncomfortable to begin with. So if you want to help yourself by putting a K, a little W, there's nothing wrong with that. Let's do some. What is the period of an oscillation that completes 5 cycles each second? So, all right, what am I doing? I'm thinking it's an oscillation. I'm going to do time versus Y position. And I'm going to have 1 oscillation, 2 oscillations, 3 oscillations, 4 oscillations, 5 oscillations. And I know that takes 1 second, because it says 5 per second. And now it says, what is the period? Well, I know the period is the time for 1 oscillation. So it seems to me that t is pretty obviously equal to 1/5 of a second, because there's 5 of them in 1 second, which is 0.2 seconds. And that's me, the visual thinker, working. That's because I like to visualize. And the other way you can do this is you can say, okay, 5 cycles each second. That means my frequency is 5 cycles per second, which equals 5 hertz. And I want to know the period. Oh! T equals 1 over f. So T is equal to 1 over 5, which equals 0.2 seconds. That's the other way. That's the abstract me thinking. That's the other way. Can I ask just a show of hands? How many people feel more comfortable with the first way? You've got to pick one of them. So I'm not saying, are you comfortable? I'm saying, which are you most comfortable with? First way, where you do the graph. How many are comfortable with that? Yeah, okay. Visual thinkers tend to draw diagrams and all that. How many people are much more comfortable with a second way? Abstract people, never draw a diagram. Remember, I'm the tester. So if you don't draw diagrams, I swear you pay a price. Not just because I'm the tester, but you pay a price because you miss sometimes interpretation. So just like in sports, if you had a really killer serve and a really lousy backhand, as your coach, I'd have you practice doing the backhand because the killer serve's already good. You practice what you're weaker at. Not exclusively. You just don't let your serve go to get your backhand better. Well, don't let your abstract thinking go to get your diagrams better, but get your diagrams better. And if, like me, you kind of think in terms of diagrams and you don't particularly like the equations so much, yeah, I got to work on the equations. It's like, you know, whatever we're weak at, we've got to find time to improve, and it will improve. How many people here do sports? How many people here were ever on a team or something like that? Whoa. How many people here play a musical instrument? How many people here have done neither? Actually, that's me. Yeah, I'm like that. So I never did sports, and I've had like 4 guitars, and you know, they get out of tune, and I don't know how to tune them, and you know, it goes on like that. I have no tenacity. So for me, the thing that taught me that I get improvement with practice was actually science. You know, it was struggling with the science, but for sports people, I've had sports people come to office hours, and what I've noticed with them is they know that if they practice more, they will get better. And I've had musicians, and musicians know that you can't play a piece when you first get it, but you practice and it gets better and better. And I think both of those groups have a kind of faith that practice makes perfect. And so I think those people are more readily willing to put up with that discomfort when they're struggling with something that's new. They don't regard it as a lack of intelligence. And I think people like me tend to regard it more as a lack of aptitude or a lack of, I can't do that. And, well, you can, you know. Of course you can do that. It's just, you got to put up with the discomfort of trying and trying and trying without any guarantee you'll get to the level you want to get at as soon as you want to get to it. But you got to have this faith that I will get better, and it's not about me, it's about how much I practice. And I really think that's a really strong skill. I wish I had more of that. I wish my daughter was more musically interested or more sports inclined. She did martial arts for a while. She was being bullied, so she did martial arts, and she got much better. She could throw me over when she was about 9. She could throw me onto the carpet, and I wasn't trying to be thrown over. She would just get me off balance. And I mean, I could push her down in the meantime, but you know, if I wasn't deliberately trying to push her down, I couldn't stand up. And she saw that improvement, so maybe that did it for her. She's a very good reader, and she's learned that I get, you know, learn more. I was a lousy reader. I read about 4 books before I met my wife. It was like, she said to me, "How many books? Have you read any of these books?" I said, "No." She goes, "God, there's so many good books you could read." And I said, "There's about 7 books before I die." It's like, you know, I haven't got that long. And then she got me a Kindle, and I read, and because I can see it better, I read more and more. I read books all the time now, and got faster and faster and faster. And my English teacher buddy said, as you practice, you will get faster and faster and faster. I remember my wife saying when she read it was like watching TV. It's just like watching TV. Just look at the page, it's like watching TV. You're joking. I'm following every word and thinking, what does that sentence mean? And now I can read not a textbook, but I can read a detective story, and I'm not aware of reading because of that practice and practice and practice. So it's all like that. So decide, you know, practice, all of it, but practice what you're not so good at a little bit harder, and it will show dividends. What is the frequency of an oscillation that completes 5 cycles per second? Well, let's draw my diagram. 1, 2, 3, 4, 5. And this is, I did that wrong, didn't I? 1, 2, 3, 4, 5. I should have done it like that. And this is 1 second. And then, frequency is how many cycles I get in 1 second. Well, I got 1, 2, 3, 4, 5. So my frequency equals 5 cycles per second, which is 5 hertz. Or I could have just said that, you know, frequency equals 5 hertz. And then what is my angular frequency? So for that, I go, I've got to be careful now. So I'm going to make a list. Omega is equal to 2 pi times f. I know that. You can wake me out of a deep sleep, and I know that. So this equals 2 pi times 5, which equals 10 pi, and it's going to be radians per second. So it's 10 pi radians per second for that one. It's 5 hertz for that one. And it's 0.2 seconds for that one. So there we have it. Okay? Not so bad. Want you to do this first one. So get your clickers and turn it on. Clickers are in this box over here. Get your clickers, turn it on and type A, B, C or D. If you have no intention of doing it, put E down, then I'm not waiting for you. So I really think you should do it. But so what is the wavelength of a wave that completes 2 cycles each meter? So what is the wavelength of a wave? Oh, I got to open it up, haven't I? Can't do anything yet. So here we have these things. So we did that the wave number was that, and we did the angular wave number was this, and we got it by saying omega equals 2 pi f, and we did the analogy of k is equal to 2 pi times the wave number, and then we just substituted it in. Or we could even get it from the diagram and draw, there's our 2 waves. This is 1 meter. We get 2 pi from the first wave. We get 2 pi from the second wave. So that equals 4 pi radians per meter. So either way, we get the same answer. When I was in college, I was taught by a professor called David Newton. Can you imagine doing physics if your name's Newton? It's like, you know. Anyway, David Newton was the nicest guy. He was a visual thinker, and he was a nuclear physicist, and there was Professor Clegg, and Professor Clegg was a nuclear physicist, and he was a very abstract thinker, and they were arguing about atomic clocks. They were in office hours, they were just talking about this thing, and so David Newton said, you know, I mean, I know that Professor Clegg's really bright, but man, he wasn't getting this. He was like just not getting the obvious, and he's clearly frustrated with me because I wasn't getting something he was going on about, and like we both wrote down what was in our heads on the whiteboard at the same time. We both like, listen, you know, and wrote this thing down, and we stood back because he goes, I was quite shocked because I'd drawn a double potential well, which is the graphical representation of the energy levels inside an atomic clock, and Newton. And Clegg had done the wave equation. And he said there were things that were so obvious from my diagram that weren't obvious when you looked at the equation. So I thought he was being a bit thick because he wasn't seeing this thing, because I'm thinking of the diagram. And Clegg is clearly upset with Newton because there's things that are obvious from the math of the wave equation that are not obvious from the simplicity of the atomic clock, you know, graph. They're the same thing, but you get different things that are obvious from them. And he said that was a big lesson for him about that division between visual thinking and abstract thinking. You'll get something either way. You get some things will be obvious from the math, and some things will be obvious from the diagram. So I'm going to pause here. So let's stop.